Alright, time for another draft physics video presentation. Pretty sure it's recording. We'll just hope so. Some more Sean Carroll, but I sort of want to get to the overview, where the big mistakes were made. Because whenever these people talk about history, they never really talk about, all of it, or they never emphasize, I think, the parts that are important. And as I've pointed out, you can go back to somebody like Faraday. Did a ton of really good experiments, figured out a lot of stuff, really good, really thorough. But he had a lot of ideas that, I think we can all know now that are plainly wrong about how things functioned, in terms he was trying to make gears to make this sense out of this thing. Like the energy goes in one place here, it does something, and then it comes out in some other form over there. There had to be some explanation for how it's doing that, how the current goes through the wire. And so he thought of a bunch of gears turning, and he could make it sort of work a little bit, but he knew it's probably not the right answer. This didn't work good enough. For everything you fix, you break something else, and that's the trick of it. I'd say he did one of the catastrophic failures was to misidentify the real force, lines of force, and being fooled by the lines created around a magnet, and thinking those were like wires or conduits for something, when no, they're just a reflection of what dipoles will do when you put them in the field. And if he could have, he sort of could have in some respects. He knew what happens if you put a north-facing magnet in the field. He knew it traced a different line, or if you put a south-facing magnet, it traced a different line, and that the line was a composite of what happens when you put two poles into the field. Anyway, little mistakes, but they're just that, mistakes, in terms of not recognizing that the fundamental functions are something where you have to start, I guess, is what I would say. So they should have thought of that with gravity. I think even Newton probably had some understanding that you could take little tiny bits of matter, and no matter how tiny I made the matter, the gravity was still proportional to the mass. It only absorbed as much mass as there was. So this was something that was really happening to the tiny little bits in something. The big thing wasn't being affected by gravity. The little bits were, and you just count how many little bits it has, and you know how much gravity it's going to have. So it's kind of a nuclear force, and once you do that, then you're back to charge again. You're back to, the functions of electrons and protons is charge, not gravity. And so maybe charge is where you should be looking for an understanding of gravity. And what happens with dipoles that are all mixed? They're not magnetic, and they're not doing anything. And so maybe that's the key to it, is that their function is the bigger picture function. And so this gets back to the whole understanding of energy, and so I just wanted to throw this bit in here. Like I said, they kind of understood what the game was. Like I said, they have a system. You put something called energy into the system, and then you get this stuff coming back out somewhere anyway. And that there's some sort of equality here. It goes into a system, and then you get the same amount of crap back out eventually. And there's no place to secrete it. It doesn't just disappear. They're sort of saying it does now, because physics has gotten so bold, and they can say almost anything. It says now that energy can go into nothing, the no space, and then it can somehow pop back out and remake particles. It's just so they're not even following any of those basic rules. So, and what they also observed was that this thing, this thing called movement or something, could be made out of two different things. It could be made out of, I take pressure out of a system, or I put pressure into a system, and that's the change. And so you have a change in a system, and it can be made by something that seems like, you're pushing, you're adding, and then there's this idea of subtracting does the same thing, that it creates movement over here that's equal to the movement over here. So if I pull something out, I have to pull something else in to compensate for it, like a vacuum. And so they should have kind of understood that this is a system that could be analogized to pressure without straining credulity at all. That and you know, once you understand that the system pressurized, that is, the system is always getting hit. There's always energy coming in, and it just happens to be that in the balanced state, that is the state that something's going to be in where it's not going anywhere. If this thing's not going anywhere, it's not going anywhere because there's an equality, okay? There's an equal amount of, it's equal everywhere. There's the same amount of stuff forcing it one way as it's forcing it another way. And that what movement really is, what change really is that I either add something, okay, or I subtract something. And that's the way you create higher or lower pressure. You break the equality by just adding or subtracting. That is, I can just put something over here that absorbs this guy, and now this is going to be changed. And all the absorption has to do is be for a moment of time. I don't have to absorb it forever. I just have to do it for some amount of time, and that's going to create an inequality in the environment. And now this thing isn't going to get hit when it was going to get hit, so it's definitely going to have some change in its motion, some change in its position. And then understanding what position would mean in this context, it means that, well, even if I do just move this a little bit, I change its position. So it was reflecting the world from this point, you know, and now I'm going to move it to this point, and now it reflects the world from this new point. That is, the energy comes back sooner. And if I do that quickly enough, I can end up with these two things, these reflections off this surface, ending up being exactly in the same place. And I can create something that can look like a higher density of pressure. Now there's more pressure here, you know, in this reflection than there is in this previous one. And I can create, you know, where there's more little bits here, and then there's only 2 bits coming off here, and only 2 bits here, but there was 4 in this moment of time. And so that can look like a wave, you know. If I can do that repeatedly, you know, where I create a little more energy, a little more reflection, because I let this sit here a little longer than it did moving. It stayed longer than it moved. Then I'll create a pattern in the reflection. And all I need is this pattern to create what I think is a frequency or a photon. But anyway, these ideas, it can account for what we see in the world in terms of it's just about pressure. It's just about moving things and moving them with certain, you know, over a period of time, and how much time you take moving things and how much time they stay in one position will change what the universe looks like. So if you have a bunch of stuff coming in, like a photon, you know, photons, hitting a surface, and just to understand that, well, what they're really doing is they're moving it. Okay, and so the other side moves with a transparent object anyway, and when the other side moves, it creates a little condensation of pressure, and maybe another little condensation over here a moment later when this one hit. And it would have the same timing and end up repeating the same frequency all over again. And, you know, no big surprises. All right, let's get to it and such. And such.
The favorite version of quantum mechanics I would like to pitch to you, but much more important than my favorite version is the idea that we should be able to understand it. It's
Right. So what we should be able to do is go through all these theories, and again, analyze which one has catastrophic flaws in the sense it doesn't cover enough, it does create impossible circumstances, it breaks conservation, some sort of basic thing, and recognize that you're not going to find the right answer by keep investing in wrong answers. I'm sorry, they just keep piling on top of wrong assumptions, and then say, well, our assumption up here is wrong. Well, if your assumption down here is wrong, then you're just as dead. You're just as finished in terms of you're not going anywhere. You're just on a road that'll go nowhere.
not mystery, it's not magic, it's just science. So let me remind you where quantum mechanics came from, why we invented this whole scheme. You know, we started out in the 1600s with classical mechanics.
Okay, so they use this word classical mechanics, where, yeah, you do experiments and you make basic observations. And again, all it takes is a little bit of thought. Again, the gravity thing, for most of my life, I wasn't thinking about it the right way because of this subtle thing you have to sort of understand, is that the force affects something based on its mass. And that's all that matters, is how many little bits does it have in it to hit. Okay, how hittable is it? That's all there is. Is there something, if I shoot a bullet at it, is there something I can hit? And that decides how much it moves. And it moves exactly proportional to how many bits I have in it to hit. And so it's the bits that are moving. It's not the big thing. It's each little bit is getting hit, moving.
Isaac Newton figured out the way the world worked according to a very simple set of rules. And this set of rules was...
So let's understand, the rules aren't rules like he made up. They're rules he discovered, okay? Like the inverse square law of transmission. And that has to do with something like point source, okay? So lots of people use this rhetoric, but I mean, the idea of the inverse square law is just simple in the sense that you're starting with a point, and guess what? An equal radius from a point is a circle. Okay, so if you have the same radius from that point, that's a circle, and it's a sphere if you do it in 3 dimensions. And the simple argument is that the force will be exactly the same there, and exactly the same there, and exactly the same there, and because the distance is exactly the same. And so whatever's happening appears to be radial, okay, from a center. And it's a good observation to just recognize that this, in 3 dimensions, is a square. It's spreading, okay? The amount of space, the bullets, if you were firing bullets, the amount of space they can cover, okay, obeys this rule that if you go half the distance, it's twice the effect. Well, I mean 4 times the effect. So half this equals 4 times the area in the sphere. So there's 4 of these boxes inside of that box. And so, 10 bullets might have hit in this little square, but now 10 bullets have to hit in this big square. And so there's going to be less bullets per square. And it just goes on and on like that, diminishing and diminishing. And light bulbs do this, candles do this, doesn't matter what it is, it does this. That most all places where you look at what the force is doing, this is what it's doing, and gravity's doing the same thing. And the interesting fact is that if you reverse it, that is, you have an external pressure, okay, of whatever, fruit flies, it just doesn't matter, heading right for a point, and that's what it'll do. Say if I have a field of chaos out here, and there's stuff going in all kinds of directions, the only stuff that's going to interact with me is going to be heading right for me, okay? So it's going to be the inverse square law of universal pressure. It's going to do exactly the same thing that the light bulb is doing, because I'm going to be a point. And that point in a random field is going to look like this. That's the universe it's going to see. It's not going to see any other universe except one pointed right at it. And so this is huge in terms of an observation. So Newton's observation, all right, is huge. Like I said, it wasn't only Newton who had this inverse square thing, but I mean, it's critical to understanding physics. That's physics in a nutshell. Is the fact that it's completely reversible, and that can be understood as a cause for why there's push away and pull towards, when pull is just an inverted push.
So good, so compelling, that the idea that classical mechanics was not right just never even entered people's minds.
So let's understand, it's classical mechanics is not right, okay? Quantum mechanics doesn't change any of that. It doesn't change the fact that things are, the light bulb is a point source and that it's radiating energy equally in all directions, essentially, in most cases. And that the implication of that is the inverse square law. And the fact is, if I go, I can tell exactly how many photons I'm likely to interact with depending on my distance. That relationship is solid, and you didn't change it with your quantum mechanics.
It was a framework in which you could do physics, and everything else from electromagnetism to Einstein's theory of general relativity fit into the.
So none of that is true. None of that fit. It never fit. Okay, and again, Einstein's relativity is a non-theory in the sense that it has no mechanism, no source. It's just saying something does something for no reason. Something moves for no reason. And it does it by the inverse square law. Now, the obvious point would be is obviously it's doing the same thing light's doing. Okay, gravitationally, as I stated in the other video, it's exactly the same as a light bulb. You could say the whole universe is lit up with gravity, and you just understand that gravity is exactly the opposite of the light bulb. Instead of shooting you with a force, there's an absence of force. Something's presence is blocking the force, and therefore it's not getting to you. It's creating a shadow. And the shadow operates on exactly the same principles.
Framework of classical mechanics. Quantum mechanics is something.
Oh, something I should have pointed out. So this is February 6, 2020. So this is, I showed you the old version. This is the new version. So whatever, 7 years later, still saying the same crap, blah, 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 blah. Except he's piling the multiverse crap on top of it.
Entirely different. It's not an improvement on classical physics. It's a replacement.
Okay, so there you say, wholesale replacement. No, it isn't. So you didn't wholesale replace any of the real concepts in the formulas, even the formalization. You didn't replace any of those pieces of those data points in the sense of the G standing for the amount of energy, and the inverse square law being critical, and the masses being critical to what the net force will be. Now, it's a net force equation. It's not a what are you causing and what's the other guy causing. We're all light bulbs, right? So I mean, gravity is, if you're going to measure what's the light in the field, you have to always account for the fact that I'm reflecting it, and in the sense that I would be absorbing gravity. So it's a net equation. But it doesn't matter. I mean, it works. You didn't replace it. You didn't do any of that stuff. So that's just nonsense. There was no mechanism in Newton's theory. There was just the outline of how the force works, and all of that is still true. And it's just a terrible thing to say. It's a wholesale replacement. It didn't wholesale replace anything. It's a silly explanation of the cause. The cause, Newton would have figured it's angels, it's God, it's who knows. He would have invented something silly because he couldn't understand all these mechanisms, atoms and blah, blah, blah. I don't know if he couldn't understand. Like I said, he had some, they knew what charge was. I'm just saying, it's not, they just didn't connect those dots. That charge has to come first. That's the elemental function. And gravity is an emergent, something that happens after you deal with the fact that the littlest bits are charges, and the charges are doing something, creating attraction and repulsion, and that attraction and repulsion is movement, and that movement is what's being absorbed by gravity.
Newton was wrong. Quantum mechanics is saying something very different, and there's no place more vivid than this picture that you've all seen, the cartoon of an atom, the Rutherford atom. I love giving these talks in England because all these things happened in England, right? And Newton, classical mechanics, Rutherford.
Right, okay, so the Rutherford atom is the only part that's implausible or unstated. So Rutherford did these famous kind of experiments where you shoot radiation at atoms. So you shoot clumps at it, stuff. And you see what happens to that stuff. So you're shooting something through a medium and you're seeing how's it changed. And so he sees that the stuff comes out at certain angles, and that once in a while something bizarre comes back at you, and so that's how he figured out how much of this stuff is matter, is because how often does something bounce back? Being deflected means, okay, it went around it and got deflected, it went by it and got deflected. But it's really, so he's just really saying there's empty space because I can shoot stuff right through. So he's just making a rough calculation of how many hard bits there are in an atom compared to non-bits. Okay, the density of the matter, and so it's not a terrible thing to say. Okay, he figured out that the nucleus is hard to hit. But it's there, and you hit it and you get a full nice reflection. When you hit it straight on in a certain way, you'll get your energy right back into your face, because it's a hard to move object. And then these electrons are really easy to move, and the only thing he did wrong was he has all this stuff swirling around, because he's thinking in terms of gravity. How do I keep this together? And he's thinking in terms of a gravitational model instead of thinking about it in terms of a magnetic model. So the real difference is electrical. I mean, they kind of go with an electrical model where they're saying electrons are excreting something by moving. Moving an electron excretes something. Something, energy is produced when you move an electron. And you're not producing energy, you're changing the position of the electron, and that's all you're doing. It's always excreting. In a sense, it's always reflecting the world around it, and all you can do is change where that reflection goes. If the electron's here, it's going to reflect light this way. If it's over here, it's going to reflect light this way. It's going to be two different results depending on which way it goes. I'm going to either get hit by a photon, or I'm not going to get hit by a photon, depending on the position of that thing. So anyway, so I'd argue the only thing flawed in the model is understanding that magnets can create relationship to each other, okay, in the sense that the electrons can repel, and then the electrons can be attracted, and the fact that they repel mean that they can't get any closer without going into more repulsion, so to speak. So, and their model is always trying to make every atom into a circle, and I don't think every atom is a circle. Atoms are shapes, and the shape is dependent on this arrangement of protons and electrons, and the fact that when you arrange them in certain orders, what you'll end up with is this will eliminate the tensions between the electrons and eliminate the tensions between the protons, because you have this catalyst in between them. So now they can get much closer. So in real terms, if in the real universe they can only get this close, these two protons, if I arrange them with an electron in here, I can get them much closer. And that's the core, the nucleus of the atom, and then the rest of the charges are in positions around the core. But there's lots of ways to mechanically understand, or attempt to understand. I mean, you could make gears, you could do different things that would work, and they never proved any of their model, and they certainly never proved any of their replacement for their model, which is ludicrous. But I'll just go through the shallow reasoning for why they say, no, it's not this way.
Rutherford did his work here at Cambridge, and Rutherford says, we knew about atoms. We came up with atoms in the 19th century, but then there was this plum pudding model where the atom was a big fuzzy thing with charges distributed inside. It was Rutherford who showed that's not right. The atom has most of its mass concentrated in the center, in a nucleus, and then electrons are very light charged particles that orbit around the nucleus. And this is still the picture you are shown today, right? We've all seen this picture.
Right, and the picture is perfectly reasonable in the sense that the external charge, the negative charges, are the ones that are doing everything. They're the ones involved in light transmission. They're involved in the creation of electricity. It's the pressure created in the electrons, the pushing of electrons, that creates all these phenomenon, and the protons are a lot harder to make move. Simply, they're much more massive, and therefore they don't go very far. And how far you go has everything to do with the field you're going to create and what you're going to reflect. If I only move this much, right, that's not much of a difference. I'm not going to change what you see. But if I move this much, yeah, well, now I'm going to change what you see.
There's some usefulness to this picture. It gives some intuition about what's going on. It's really the electrons that...
It gives intuition. I mean, even that's no, it's the byproduct of deduction. Okay, I mean, in the sense that it fits, it works, it explains the experiments. And again, experiments kind of obvious. You're saying, well, if it's a plum pudding, then I'll hit it all the time. So obviously, it can't be some solid thing. It has to be something made of constituent bits, because I can shoot stuff through it, and sometimes the stuff goes right through it, and sometimes it doesn't. And so clearly there's a probability of interaction, and the probability has to be connected in some way to how much stuff I'm making it out of, how thick it is.
They're doing all the work in something like chemistry or electricity in a material or something like that. The heavy nucleus just sits there. The electrons can jump from atom to atom.
All right, so the jumping from atom to atom is, that's one of those things where they're making sort of an assumption that the electrons actually do go somewhere, when maybe it's just the pressure between them. An atom has its electrons in pressure. They're sharing an electron, and the pressure ends up going into the other atom because of that pressure. The electron just pushes. It changes its location. As I've said with the ping pong paddle analogy, you put two paddles together and there's a certain amount of pressure if I have a ball that's perpetual between them. And if I make it twice half the distance, then there's twice as much pressure. Well, if there's another paddle over here, he's going to feel that pressure.
But I'm here to tell you this picture is nonsense. It is not the real world, and I can tell you why it's not the real world.
So they're making emphatic statements, and you won't tell us in any detail. You won't show us a ton of experiments that prove it. You won't do any of that stuff. You're just making this assertion that we've all sort of agreed to forget about this model and believe in this one over here. And there's no reasoning. Well, like I said, the reasoning provided is so trivial.
Because, as I alluded to, in the 1800s, people like Michael Faraday invented something called the theory of electromagnetism. James Clerk Maxwell especially put the finishing touches on it.
So there was no theory. There was just mathematical equations that basically defined relationships that exist between converting one into the other in terms of an effect that magnets and electricity share a common mechanism. But there was no formalization of a model. Again, Faraday's model was gears. Okay, I mean spinning gears. So for him to say they had a model that came along where they got an understanding of electromagnetism, they didn't have an understanding of the mechanism. They understood the relationship, that if you moved a magnet, you could move electrons in a wire. That's all.
And according to that theory, if I have a charged particle like an electron, there's an electric field coming out of it. Okay, so that's according to the theory. So what the theory is saying is that there's two kinds of charges, all right, the proton and the electron, and that they have this inverse relationship. And that's what they could figure out, is that they attract each other, but they repel the same. So if the opposites attract, the sames repel. All right, so if I put two magnets together and I do this with charges, I get exactly the same result. So that's all they understood, is that and that it's point source. So it's not so much that electrons are actually producing something, it's that they're reflecting something, and that electrons are reflecting something exactly the opposite. So again, I could just make these two colors and just say there's purple in the universe, okay,
And what do electrons and protons do? Well, the proton reflects the blue, and the electron are red, and the electron reflects the blue. So all blue reflects off an electron, and all red reflects off of a proton. And all I can do is I can just say the other color just goes right through the electron, and the other color goes right through the proton, and it'll work. That simple mechanism. And then you'll get all of these effects with magnets. You'll explain why there's a difference between them, and you'll figure out that if I have just an electron in the universe, it's going to reflect purple because the red will go straight through and the blue will reflect off, and you won't be able to tell the difference. You won't even know it's charged. But if I put an electron in there to test what color what its real color is, I'll find out, because these two things will end up reflecting right back at each other constantly. And they'll create pressure between each other, because they're going to take all of the blue that hits this one is going to reflect back to that one. And just like bringing the ping pong paddles together, I'm going to end up creating a great deal of pressure between them, because now I'm going to see that they are reflecting the blue and that the red is just going through, and it's irrelevant to both of them. The inverse and all of that. So there's simple models that explain it, but they didn't explore anything. They're just saying, we know this is what it's really doing. So their argument is they know that somehow electrons are at work. Electrons are working. They're not reflecting a world, they're actually producing something, and they only produce it when they're moving. So when they're staying somewhere, they know there's still a charge, but they're somehow saying that when the charge is moving, that means it's doing work. So the electron staying still and reflecting or producing its field doesn't mean anything, but somehow it's moving and producing a field in a new location. It moved from here to there. Somehow that was work. We never called that work anywhere else in the universe. There's anything essentially different it's doing, so why is that work? And why does that mean the electron has to slow down and die and fall into the nuke? No, it doesn't have to do any of that. So this is almost a silly excuse to bail on a rational model of the universe.
So if I move the electron a little bit, the electric field shifts to point toward where the electron is.
Right, so you could say, so what? Does that work? I mean, did the electron have to do work? Or did it just have to be pushed, like anything else in the universe? I throw a magnet into space, or I throw an electron into space. I mean, what's the argument? That it's going to get tired? Says them. I mean, I'll argue that it's going to get dragged, but that's completely different than the argument he's making.
So if I take the electron and I shake it up and down, there's a wave that propagates out from the electron, and we call that light.
Okay, so let's understand. That's what you'd say. It's not just one wave. It's supposed to be two waves somehow. A magnetic one also. But so there's just no explanation. But obviously, as I'm pointing out, moving something does change things. If you understand that there's a world full of light that's bouncing off all the surfaces. And the truth is you can see it. If I move my hand forward and back, I'm changing in a way the density of force that's actually hitting you. So if you thought of the atmosphere being full of some kind of thicker stuff that I could push, like with each time I pushed, it created a bulge. I mean, you can just get the idea that if I change its position, I change what's going to move off of it. I guess it's not the same to use a medium because we're talking about stuff that moves the speed of light, but anyway.
We call that electromagnetic radiation. All of the light in this room comes from shaking electrons up.
So he says so. So he's quite confident that's the truth, that electrons shake. And that creates light. When it's not an electron shaking that creates a photon. It has to be a bunch of electrons doing that. And because we already know that, because the polarization of the light is huge. The amount of this vibration, the thickness of the vibration of a photon of light is huge, thousands of atoms high. An electron can't be vibrating thousands of atoms high, right? So we already know this can't be the right answer. That's not what's happening. That's not what's creating light or photons. I mean, it's just overtly unresolvable to the facts. The facts say we know that photons have a polarization. Their polarization is gigantic. How does this explain it? It doesn't explain it. It leaves it out. It just ignores it. It's a bad theory.
And down and watching the vibrations distribute in all directions.
So again, distribute in all directions, says him again, in the sense that, that would be true if I can push something into the field, no matter where I put a charge, it's going to be changing what all directions will see. Every direction will see that the position has changed, so there'll be a change in the field everywhere. But that's not what a photon is. That's demonstratable by something like a laser beam demonstrates it.
Guess what? This picture has an electron zooming around in a circle. It should be emitting electromagnetic waves.
Okay, so we already know it doesn't. So see, he says, well, it should be making these waves. Well, it really wouldn't be making a wave. Like I said, it's like going back to Einstein's theory about gravity waves. The wave would be so subtle in the sense that all you're doing is if you're moving this electron quickly enough, around and around and around and around, the speed of this tiny orbit would be imperceivable in terms of this is moving the speed of light in this tiny, tiny, tiny circumference. I mean, obviously the amount of change it would be creating to the environment would be so minuscule that nothing could ever detect the fact that there's a change in its position. And the subtle argument with the gravity wave is that there's a subtle change in the precession of the center of its gravity when you do this. This alignment has less gravity because it's spread this way. For somebody looking from here, right? Somebody looking from down here, looking up at this spread dilutes the gravity, where this spread intensifies the gravity, but it's minute change. And so all it's really saying is that the object appears a little bit closer when they're in line, and it looks a little further away, okay, when they're parallel or whatever, tangential to that. But it's tiny in terms of the change in the universe and wouldn't account for electricity or any of these effects.
Be emitting light to beat the band. And that means the electron should be losing energy.
So again, there he said it, right? So it's doing the same thing it always does, which is makes charge, being charged. It's charged. It's always charged. The charge bulb never turns off. And all you're doing is moving it. So he's saying that something innate about taking a light bulb in space and then I put it in gravity, and the light bulb is making its light, it has a little battery, it just makes light. And it does that whether it's standing still or whether it's moving in orbit, doesn't matter, it's always making light. And he's saying somehow it's running out of energy, the moving is somehow causing the battery to go dim. I mean, there's no continuity to this argument.
It should not stay in a stable orbit. It should actually spiral toward the center of the nucleus. And that should happen very quickly. You can run the numbers. You can do the math.
Right, yeah, right. You can do your math based on your wrong assumptions and your silly mechanics. That somehow the electron is responsible for creating its motion. That somehow it's not like every other thing in the universe that just moves. No, it somehow has to make its movement where you're saying nothing else has to. So nothing else is responsible, right, for moving. The bullet, we know, moves because I put a bunch of gunpowder in its butt and shot it out of the gun. We know why it's moving, right? But the electron, we're saying he has to account for moving. He has to create his motion. And that's just nonsense because you don't apply those same standards to anything else in the universe. Why does the electron have to do that? And again, it's just because of this wrong assumption that they think any movement in an electron is somehow a photon. And a photon is more complicated than any movement. The photon requires the electron to move in a specific way to create a specific frequency. And that's the photons we see. And yes, every time it moves, it's creating some kind of noise in the universe. But it's not noise that's going to be a photon. It's not going to be the specific energy it has to have, the specific frequency it has to have, not energy, to be visible as a photon. So yes, it's creating photons all the time. They're just not of a frequency you can see.
And showed that it takes about 100 billionth of a second for the electrons to go from their orbits down into the center of the nucleus.
Right, so this might even be another reason to say, well, look, if you have math that proves that, then great. Okay, it doesn't prove anything. It doesn't. The math is full of assumptions. Then why don't you say, well, what if we just let them stay here as charged objects in balance? That is, why don't we just balance the charges, and let's say that's the atom. The atom has a balance in its charges. The electrons hate each other just enough, and the protons hate each other just enough, and then the two opposites are attracted, and I can just balance the attractions and repulsions. And nothing has to move anywhere. There's nothing spinning around anything. And when they're sharing an electron, they're really sharing it. The electron isn't doing a figure eight or any of this crap. It's just sitting there, and both of them, both the nucleuses of the two atoms, are feeling the attraction of the electron and are connected to that piece that has low pressure, that's creating low pressure in its field and saying, move towards me.
So here's an experiment we can all participate in right now. We can ask, here's a table, there's atoms in it, here's you and me, there are atoms, and I predict that if classical mechanics is true...
So isn't this like such a straw man, disgustingly straw man argument? Let's accept all my silly premises and then say you said that. So he's putting in classical mechanics' mouth his silly assumptions about how an atom is structured or formed. And, and this is not an experiment. He's mocking the whole process of experiment. Like, this is really your evidence? Your evidence is this pitiful? You're going to pretend first that classical mechanics said something they didn't say, and then you're going to sit there and pretend that because I proved what they didn't say didn't happen, therefore they're wrong and I'm right. It's pitiful.
100 billionth of a second from now, they will all collapse into a point. Ready? There. It didn't happen. So there's something deeply wrong about classical mechanics.
Right. There's nothing deeply. So it's just such a straw man, obviously. And he would say he would do this. He would. Let's say Rutherford and Maxwell and Faraday and all of the Huygens, all of these people, all these really brilliant people were sitting in the audience, and they all had different theories, and they all pondered this question for years and years and years of their life. Would he pull this kind of trick if they were in the audience? This kind of shenanigans, and say, there, I've debunked you with this brilliant argument where I put words in your mouth, okay, that you never said, and then prove those words were stupid. Wow.
It took a long time, took a lot of smart people thinking in different ways to come up with an explanation of what might be going on.
No, to come up with an excuse to forget about the rules of science, where you actually have to prove something, and you actually have to repeat an experiment, and you can't be doing all this, let's way jump the evidence, and let's really just turn physics back into a religion. And that's all they've done. They've just turned it back. They've just gone backwards and created a bunch of voodoo and snake oil.
Here's the explanation they came up with, and it's really dramatic, and even though it took a while, to be honest, it's amazing that they came up with it as quickly as they did.
Oh, amazing. I know, it's silly. It's just silly. So now we're going to go to the, so we can't see these things, right? We can only see their effects. We can only measure them indirectly at best. We can get some indirect knowledge of their function. And so now his simple solution to the quandary or the circumstance is just to say, well, we can't see where it is, so let's just generalize and say, in a certain time period, over averages, it's always somewhere like in here somewhere. Okay? Well, I can't see where it is. But, if I test, I'll find it here, and I'll find it here sometimes, and here, and here. And there'll be a certain probability, and I can write a silly little symbol, and say, there's the probability factor, the wave function. When all it is a generalization. All it's really saying is I know the dice have these different numbers on them, And I know when I throw them, okay, there's a certain probability of certain number arrangements coming up. And that's all they're saying. And because that's true, I'm now going to assume that you don't have to throw the dice and hit a wall, and you don't have to do this, and you don't have to bounce it off of here, and you don't have to do any of that crap. Okay, just sit here and watch them, and there's a probability that they're going to do something. I mean, it's so bad. They're just saying, forget about the idea that the dice are actually dice. You know, and they actually have 6 sides, and they actually have a number on each side. And we know that. And we know that there's going to be probabilities of outcomes for what you put in. You're going to get certain probability of an outcome depending on how much you can randomize their functions. And that's all there is. But there isn't any truth to this notion that the electron isn't in a place and it isn't doing a certain thing. You know, because you can generalize, because you can make a general statement and say, over different encounters with atoms, I can find them in certain locations. Well, so what? That doesn't prove they're not in specific locations. Just as when you get a 6 on the dice or a 4, doesn't mean it wasn't a 4 for a real reason. And the reason started with how you were holding the dice when you threw them into the randomizer.
The explanation is that electrons are not particles. It's a pretty dramatic explanation, so I wanted to think.
So even if you don't use this word particle, the idea that they're not a discrete thing in a discrete location is what he's saying. So we just decided that we're going to pretend electrons, which are very reliable in their location to have function. You know, I mean, realistically, can you imagine that electrons don't have to be specific things and then still think that light could get through a piece of glass? I mean, it just doesn't make any sense that it's amorphous or undefined. It's a real structure. Crystals are real events. They have real alignments. Domains, magnetic domains, have real alignments. They don't have fake ones. They don't have, I think I'm this way or I think I'm that way. I mean, it's a real universe with real structures in real locations. And this is just such a this is an extraordinary claim. And does he have any evidence for it? That he is going to provide us a huge pile of evidence showing us how this must be the truth? No. He's just going to say, I have this theory about the smallest things in the universe, the things we can't see. I say they're gremlins. And that's it. They don't have any evidence they're gremlins. They're just saying, I can make gremlins mathematically work. Well, of course you can, because they can do anything you want them to do. Just as your wave function isn't a standard function, right? They keep talking about like it's a real function, a real thing. No, it changes for every single circumstance. So if I'm rolling dice, different wave function. I'm doing something else, different wave function. I mean, this is just such crap.
Again, that electrons are deep down, they're really waves. Rather than thinking about the electron as a little point moving in an orbit like a planet in the solar system, you should think of the electron as a cloud, a wave-like cloud.
So a wave-like cloud. So even if you were to say that you're trying to think of them as a wave, all right, I mean, even if it's possible for you personally to make that make some sort of sense in some way, the fact is that your wave would have to have a frequency, right? So you're basically saying your electron is producing something that's whatever, doing this kind of thing, blah, blah, blah. It's just this thing that's sending out this lump, this wave, okay, this lump in the medium, every location. There would have to be a frequency to it then. There's no frequency to an electron. There's no constant frequency it's producing. It's a charge. Charges do this. Okay, there's no frequency to what a charge does. There's no frequency to magnetism. Okay, they're not waving. They're not sending lumps of energy. They're not sending waves to something. They're constantly streaming, constantly shooting. Like a radioactive element. The little rays are flying off. They're just flying. And there's no consistent frequency. There's no wave. There's none of that. there's just a constant shooting of little bits of energy, little bits of energy, little bits of energy, little bits of energy, quanta of energy in all locations, at all distances. There's no wave. There's no evidence that electrons wave.
Concentrated near the atomic nucleus. And for those of you who are tortured by chemistry classes as college students, you recognize these orbitals, which are the different shapes that electron wave can take. Just like if you have a string that is tied down at both ends and you pluck it, there's sort of a fundamental frequency, then there are higher harmonics. Likewise, the electron
are half and quarter and eighth size waves. Yes, they can fit into something and be constructive. So again, that's just this idea that you can't add energy to a pendulum that's swinging. I can't add energy to the pendulum swinging if I hit the pendulum when it's moving towards me. I have to hit it when it's moving away from me. So I can obviously have energy going at a frequency, and as long as the frequency is twice, okay, the swing, then I'll always hit it where I need to hit it to add more energy. And those would be the harmonics that are constructively capable of adding energy. But that has nothing to do with these orbitals for their electrons. And just again, the whole idea is this is supposed to be stuff that glues stuff together. Atoms stick to each other because of this. And to think that there's this, again, these silly patterns they have, these things traveling at, how would that hold atoms together? It's illogical to think that I could have the electron over here, and I got a nucleus here, and I got a nucleus here. And I can have the electron over here, and these two nucleuses would say, I'm just going to wait until the electron's over here again. No, it's not going to wait.
Wave has its lowest energy state and then various higher energy states where it looks more complicated. So the reason why...
So energy states are just the pressure of the geometric arrangement. So, I shouldn't have to go through all this stuff. I mean, it's just so easy to model. It's just geometry, I mean, it's that simple. So you can take a system. Now, again, the more rudimentary atoms like hydrogen, again, I'm going to argue that they're very simple in terms of arrangements. They're not spherical. But more complex atoms are made of those in terms of how the nucleus is arranged with the electrons. But the simple idea is if I had 4 electrons around something, you'd understand that there would be a balance between these. The electrons are repelling each other. If I try to move the electron in closer, you can understand that makes it closer to the other electrons, and that pressure is going to push it back. And so there's a balance. And then if I was to add some more electrons, I would have to add them in places where it would also balance the pressure. So when they talk about energy levels, all they're really talking about is the fact that there is pressure, okay, depending on the geometry, will create a certain amount of pressure that the electron will be in terms of the balance between the attractive force and the balance between the repulsive force of the electron. And that's what's really saying what's your energy level. The ones that are going to be in the tight pressure are going to be the ones on the inside, and the ones going to be on the loose pressure are going to be on the outside, I think, kind of obviously, because of the distance from the proton. So the ones that have the high energy level are the ones on the inside.
The electron does not spiral in and collapse to the center of the nucleus is because its lowest energy state is not sitting point-like at the center, but being spread out like a wave. Okay, circa the 19th...
Spread out like a wave. Again, just to make any sense, all waves have to have frequencies. The electrons have no detectable frequency. That's just mush. There's no frequency. There's no wave to its function. There's no wave to its existence. It's radiating a force. And the electrons radiate opposite force from the protons, and that means that they attract to each other and they repel their likes. They attract their opposite and they repel the sames.
In mid-1920s, people came up with this idea. And you can actually explain data using this.
So what? You can do it using the Gremlin theory, the angel pushing on the earth theory. All of those theories work too. And they're just as equally unevidenced, and they're just equally as magical. You're just making up a fake entity, a fake mechanism, and saying, look, the fake mechanism works. So what? It's fake. You invented it. You didn't discover it. You invented it.
Explain why the light emitted by atoms has a certain form. Even better, there's an equation. It's important that I show you the equation because at the quiz that will be handed out at the end of the lecture, you will have to do some problems. Sorry. This is the Schrödinger equation invented by Erwin Schrödinger.
Okay, so the important thing is the little stupid, whatever it is, the knife, the three-bladed knife. That's not a thing. That's not a constant. Okay, there's not some way. That's called the wave function. But it isn't a real thing. It's not a like one number. It doesn't like you don't go solve it and just say, oh, okay, that's number 76. No, it changes for every single system you're judging. So what you're doing basically is you figure out there's 6 sides to the dice and there's 2 dice, and you figure out exactly what the probability is, and then you call that a wave function and say, there, the wave function solved the equation of how probable it is. No, it didn't. It's just a fact of the amount of variables there are. There's only a 6 side. There's only a certain number of possible combinations. And the wave function didn't figure that out. You figured that out and put it in the wave function. So it's just completely a bogus notion that they have a universal equation. There's nothing universal about this equation. This can't work everywhere because every single circumstance you're going to change what that little knifey thing what that number is.
And actually, we're not going to go through the details here. The point is that there is an equation. It's very pretty. It's like a little piece of concrete poetry, if you want to think about it that way. But the point is that not only do we have an idea, electrons are waves, not particles.
So, yes, it's an idea for which they have absolutely zero evidence. So, this is the de Broglie thing where they've now done this, though. They've said frequency is energy when it's not. Frequency only means something when you're going to try to push something out of its tension, when you're going to try to tip something over. Frequency matters when you're trying to tip something over. Frequency doesn't matter if all you're trying to do is move it. If all you're trying to do is exchange energy, it doesn't matter what frequency it is. You can balance or imbalance the system all you want. But if you need to imbalance the system in one way to make something happen, a trigger, to pull the trigger all the way, because it's a little bit tight, you need a certain amount of energy in a certain amount of time for that to take place, and that's where frequency matters. But it doesn't matter in the real universe. In the whole universe, frequency isn't energy. But they've made them synonymous.
We have a new equation to replace Isaac Newton's equation. Isaac Newton's equation is F equals ma, force is mass times acceleration. You tell me where...
And there's nothing wrong with it. It's completely rock solid, and you don't need to change anything about it at all. And all they're going to basically say is they're going to change that F into a F for frequency.
Where a particle is, how fast it's moving. Newton's laws in classical mechanics will tell you what it's going to do next. In quantum mechanics, you tell me the wave function, very boring name, sorry about that, the wave function of an electron. Schrödinger's...
So the wave function is just the probability function. It's just establishing what are your outcome possibilities. And that's it. And then it's going to, it's not telling you anything significant, except the fact that there's a probability and that if you do it enough times, it'll come out to the probability.
Equation is going to tell you what it does next. On the right-hand side of the equation, it asks how much energy is there in the wave function. On the left, it says here's how fast it's going to evolve over time. So that makes physicists very happy. Equations are what make warm their heart a little.
Yeah, because it's a way of evading a model. It's a way of evading having to actually realize that physics is about physics. It's about physical things doing physical things. And the major thing that's happening in the universe is motion. And things exchange their motion. And that's all that's happening. Force is motion. Motion in, motion out. There should be equations that are balanced because the motion has to be conserved. So little things move, then big thing moves. A little Putian people, they all run and push on Gulliver or whoever the fuck it was, and they roll him over. And there's an equation you could write for how many little people it takes to roll one big person over. You know.
A bit, because it's full employment, really, for physicists. And it's certainly full employment for physics students. Solving the Schrödinger equation keeps them up at night when you're second-year undergraduates doing your quantum mechanics. Here's the
right, because the real catch is the equation requires you to figure out the probabilities ahead of time. You have to figure out what is possible. What you have as an outcome. What are the outcome possibilities? That's the hard part.
The problem. Exactly because you have an equation and the equation is unambiguous in what it says happens.
So this is again silly. It's very ambiguous until it finds out there's only 6 sides to the dice, and so you can only have an arrangement of those 6 sides, and that's the outcome. And once it figures that out, then it's very unambiguous in the sense that you know that the likelihood of each combination is the same. Well, not by number. Obviously, you can make a 7 with a 3 and a 4, or a 6 and a 1, or a 2 and a 5, and blah, blah, blah.
Say, not just for electrons and orbits, but for any phenomenon, period, the Schrödinger equation should apply. If you're saying that quantum mechanics is a fundamental replacement for classical mechanics, you can use this equation to make all sorts of predictions.
Right, and predictions are just based on probabilities, and that's based on learned experience. Learned experience says this chalk will not jump to Venus. Just won't do it, on its own, unless I have some reason, I'm adding something to the system that gives it that probability. Like I'm shooting a gun, Then there's some chance that the piece of chalk might go to Venus, right? That I might actually be able to take all of the forces going in different directions inside the chalk and move one piece of the chalk really, really fast by hitting with a bullet. And one piece of the chalk might go to Venus because it might escape Earth's orbit and fly through space. But I have to have a mechanism. I have to have the energy in. And then I'm just going to decide what are the different manifestations. How can it affect this in some way where all the energy goes in one direction? And is it possible? Well, it's possible, but it's not very probable.
Here's a kind of quantum mechanical phenomenon. A nucleus of an atom might be unstable, right? It decays. And when it decays, it might...
So this is this magical decay, right? So again, it's another thing where they don't say anything about what decay is. And, they never go through the details. So the things we've learned. And some of the things we've learned is that decay can be accelerated. That things don't decay at some kind of standard rate. Okay, so if I do take 2 uranium atoms and I put them close together, all right, I take their 13,000 year decay rate, okay, and I make it 5 or I make it 2,000. I change how fast I can expect these atoms to degrade into thorium and whatever, hydrogen, helium or something. So I can take this uranium and I can manipulate its decay rate. And the logic kind of tells you that what is its decay rate, right? Is it something it's born with, like it was born with a certain lifespan? And so I could say that, well, this uranium came from 13 billion years ago, and this uranium atom came from just like 6 billion years ago in a sun. So they have different ages, so they'll decay at a different time. And, that's kind of an unlikely expectation that each uranium atom was made in a different sun. And, that's not too likely. It's more likely that it came in clumps. So that's not going to work. It's a theory I liked at one time, but yeah, it doesn't work. And it doesn't explain why it's accelerated. So what I would argue is what's really deciding it is a probability, right? It's just a probability equation. You're saying how probable is it for the event to happen? So it's some sort of unlikely event. So I could say, well, no, Jedis, 2 Jedis have to swoop into the atom at exactly the same time, and there's a mouth and a butt to the Death Star, and they have to shoot a little bit of force has to go in both of those inlets at exactly the same time, and it has to meet right in the center. Bingo. Okay, then the atom splits into a thorium and a helium, and therefore you have your nuclear reaction with a bunch of extra bits left over that create light and all kinds of other radiation. So it's just an event, and you can change how likely the event is because if I put it into a field, well, then there's going to be more Jedis flying around, right? The more Jedis hang around the atom, so there's more Jedis. If I put more uranium atoms together, there's more Jedis, and so now there's more likelihood that they're going to do this coincidental shoot at the same time thing. And I could also argue that if this was an atomic clock, I could argue that, well, when I'm moving the atom, right, if I start moving it, and I'm moving it with this hole and this hole in the direction of the movement, well, it's going to be more likely that I get shots this way, and it's going to be a lot less likely somebody shoots this way. So I'm going to make this decay slower. Okay, it's going to go from 13,000 to 26,000. Okay, because I'm moving it, I'm making it less likely for somebody to get here in the middle at the same time. So I mean, you can come up with explanations that make it work. That this is a model. Okay, this is what a model looks like. What they're doing is just talk. Right? It doesn't have any mechanism. It doesn't have any structure. They just have this amorphous stuff. Though the blob of wave does the blobbing over to the blob and the blobs, and then it pops out of space, and then, I mean, it's all made out of magic. There's nothing physical happening.
An electron or another charged particle, and the Schrödinger equation will predict how that electron gets emitted. Remember the electron?
All right, so again, the equation doesn't predict anything. It has to first figure out, oh, it takes 13,000 years for the atom to decay. It has to figure out how improbable it is before it can figure out those futures. So the equation does not solve for probability. It will not tell you what the decay rate of uranium is. It doesn't tell you that. You tell the equation that. You have to give that to the wave equation. You have to give it the answer before it can give you an answer.
The wave, the way it gets emitted, will look more or less like these. It'll be like some big spherical cloud that moves away from the radioactive particles.
Again, this is just a simple math trick in some ways. So I mean, it's not like this is a complex math trick. This is the Feynman math trick. Okay, it's just understanding that they turn probability into a vector, okay, an arrow, a length, okay, and a direction. And then they say how probable is something, and they can add those arrows, and then they take the square of the distance, right? So they just square this stuff, and they figure out these are your inputs, okay? This input squared will give you the area of this squared. So it's just Pythagorean, for frig's sake. It's nothing fancy. They're just saying, these are your potentialities. These are your variables. This is your outcome. And that's just a probability equation. That's just going to tell you what's the probability of a specific outcome will be dictated by how you add these two vectors. And that's it. What vectors you're adding. What vectors in time you're adding will tell you what's the likely outcome. And it's basically just saying if I have something tipping back and forth and I shoot something up straight, what's the outcome? What's the likelihood of it hitting and ringing a bell? And that's what the things you're squaring are those likelihoods. The percentage of time the thing is in this position. So one of these is the percentage of time it's in this position. And the other one is how often you're shooting. And that'll give you the square will be how probable is it you'll have the outcome you're looking for. You just put the variables in, take the square as your outcome, that's your probability. It's probability math.
Here's what it actually looks like. This is a real picture of a little bit of uranium in a cloud chamber that is emitting radioactive particles, and when the charged particle moves through the chamber, it excites the atoms around it, and they...
Right, so there's just absolutely no admission. Look, I'll show you what the evidence says. That's completely different than what I'm saying. I'm telling you there's some sort of wave coming off of these things and all this other stuff, and clearly there's no evidence of that happening. Now, yes, a cloud chamber is a little complicated because the light you're seeing isn't coming from the particle. It's coming from the particle hitting atoms, and the atoms are creating the photons. So you're not really seeing, nuclei shooting or electrons shooting. You're seeing what the atoms that they're hitting produce?
Leave a little track, okay? So these little trajectories represent particles.
I mean, you have to understand that every time one of those impacts is happening, it's essentially saying that, you know, the electron is actually hitting another electron, or the gamma radiation is hitting something and moving it, or the nuclei is hitting something, pushing it, you know, and the atom produces the photons that you're seeing. Well, it's not even that they have to. Actually, the photons you're seeing are really reflected light off of the physical change in the atoms. So the atoms have physically changed. They've, you know, moved in some way that makes it possible for us to see radiation bouncing off of them. But I mean, we're not seeing the electron. We're seeing, well, I already said it.
Emitted from the radioactive substance. What you immediately see is that they're all straight lines. They're trajectories. It's as if a particle...
Right, and there's no evidence of a wave anywhere. There's no evidence of a bunch of them getting together and creating a wave that goes out through space. There's no waving. Even as a collection, they're not waving. There's no wave in here anywhere. It's clear, and that's exactly how you should see a charge. That's what a charge is doing. And the two charges, the proton and the electron, are just emitting completely different colors. They're reflecting them differently. And so, and again, but you can only see that when I put two of them close to each other, because then you'll see the blues start reflecting in one area, and you see that the red dissipates. And, you know.
Particle has moved through once it was emitted from the radioactive substance. That is not what is predicted by the Schrödinger equation. The Schrödinger equation says there should be a wave, big puffy thing going out in all directions. What you see when you look at it is as if the electron looks like a particle. So it's almost as if the electron is kind of like a wave when you're not looking at it. But it's a particle when you look at it.
All right, so you should know right there. Isn't that enough? Isn't this too silly? I mean, this is all they really have. It's just I just made up this theory. I can't show you any evidence of this wave thing because there is no evidence. I can show you simulations I make up, and this thing's going like this, and there's this peak, and I can show you fake stuff, but I can't. He can't show you anything real that demonstrates any of this is happening where somehow this force is moving in some amorphous, entangled way. I'm entangled. I'm superimposed. I don't know where I am. Blah 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 blah. And you know, when we do look at it, no, it's not doing any of that. It's going from point A to point B to point B to point B to point. You know, it's just going through its different points and exactly by certain rules. And Feynman can draw you diagrams where it'll go exactly. And I mean, they see all this stuff move in exactly straight lines. Why are they pretending it's not really in that straight line? Why are they pretending that when they see that you know there's no line, but they see this thing shoot something out, that they don't know that something went in exactly that way? That's the math they actually use. They don't pretend it came in this way and this action happened. They know it has to be conservational. They know we can't break these rules. I mean, this is so bad.
Okay, so in the late 1920s, the greatest minds in physics thought about this. Einstein, Bohr, Schrödinger, Dirac, Pauli, Heisenberg, and they came together, they had meetings, and they fought and everything, and they came up with a theory of what was really going on.
So there's more nonsense. They didn't come up with. No, there was a real fight, okay? There was lots of arguments about how this is incomplete and this is underdone, and you haven't got it yet, okay? You don't have the elements of this right. There was no agreement, so this is more nonsense. There was some agreement somewhere. No, one club of putzes won a popular vote, and that's all that happened. And they weren't right.
Their theory is the following. The electron is like a wave when you're not looking at it, and it's like a particle when you look at it.
So again, that wasn't what Einstein said back then. And, you know, later he conceded, okay, because the rest of physics seemed, you know, it obliged him to play along. And so he made a weird little statement where he said, yes, it appears that this is the way it is, blah, 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 blah. But it was, you know, you could just see his heart wasn't in it.
Sadly, this is the state of the art, even today. And it's called the Copenhagen interpretation of quantum mechanics. So the way that we resolve this apparent paradox is to say that the electron over here on the left, it has a wave function. It's a
Right, so it's not a real thing, okay? It's not an electron until it interacts with something. Then it becomes an electron. But we know factually that it did exactly. We can run it backwards. So we can run it backwards. We know it went from point A to point B, and then it was at point C. We know exactly where it was. It left its fingerprints every single place it was. We know it went in straight lines, but it didn't have time to go in any crooked lines. We know it was moving the speed of light. So where is there anything to account for this superposition? This fact that it went this way, and with these paths take much longer to go, obviously, these other paths. It couldn't have done all that. There was no component doing any of that. The only thing that happened is exactly what we can retrace. I mean, there's absolutely no reason to believe in this woo.
spread out kind of thing, some kind of cloud. But then when you look at it, the wave function changes.
So again, it's not when you look at it, it's when it interacts. Interactions define a point where we have some chance to see something's existence. We can't see it till it hits something. It's like a photon. You can't see it. It has no existence in the universe as far as we can tell. It physically doesn't do anything until it actually hits an electron. That's it. They only exist when they hit electrons. And they're just making up this story that this photon's doing something very complicated and very mystical while it's in space. But the point is you can always trace its path in a straight line. You can always find a path that works, a straight line path. No wave function necessary. And he's just saying, oh yeah, well it went every possible direction, and every single one of them created a new universe. And he even goes into the silly. I can account for the creation of the new universes. I don't need any more energy. Somehow the energy that's already in the universe is enough to make a duplicate universe, which is so preposterously silly a statement. It's just pathetic. Because they all have the same root, you see, and the root universe was huge. That's their excuse. That half of the new universe is the old universe. You get it? Like when you're making your new universes, half the universes, you're sharing the same past universe. You don't have to make a whole new universe with a whole new history. You get to take the old history with you, and you can make the old history infinitely big. So no problem. You have an infinite amount of past to make your infinite number of futures out of. Gee. And this is the kind of crap. They say, oh yeah, mathematically proven. That if I put an infinite amount of stuff in, I can have an infinite amount of stuff come out. Well, yes, I can mathematically prove that. Oh, how brilliant. Well, anyway, enough of a video, I guess. It's just so bad. I mean, I might as well play a little more of it.
Suddenly, dramatically, and unpredictably. You don't know exactly where it will change, but it will collapse onto a point, so it looks like a particle. And the best thing to say...
And we know he'll do it exactly by the probabilistic rules. The snake eyes will show up as much as the boxcars. Those things will have exactly, they're right next to each other in terms of peaks. They have the same height of peak. And they'll show up just as many times. Oh, it's just so bad.
Is to predict the probability that the location of that new particle will be here or there. And the rule is, the bigger the wave function at any one point in space, the higher the probability that the particle will be found there. Okay.
So again, they're just saying right to your face, they're saying, this is like Feynman, right? You're saying, okay, I'm watching somebody throw dice, I watch the outcomes. The outcomes are probabilistic, they obey the rules. And Feynman's basically just saying, don't bother calculating how it bounced and what it did. That didn't create the outcome. The outcome was created by random. It was just a random thing that happened. It didn't matter where you threw it or how you threw it or any of the physical mechanics. No, because everything was just a blob of probability right from the start when you're holding the dice. And it has nothing to do with the physical interactions. It's just a terrible pile of nonsense. It's hurting me to realize just how pathetically stupid this all is. And I'm having to have this conversation with people that have some sort of IQ. You have some sort of intelligence. You've been in the real world for a while. You've heard these silly religious stories that the whole world is still somehow convinced by these silly, stupid, jackass stories. You've heard about fables like, oh, the emperor's not wearing any clothes, and the frog and the scorpion and all kinds of little things, and you get some notion that the real world is a little bit tricky. You can't take everything for granted. You can't just believe crap because people are lying scum. And you're falling for this shit? And it's shit. There's no fucking evidence. Oh, God. All right. I'm done. You people are disappointing me.